السلام عليكم ورحمة الله وبركاته. كيف الحال يا شباب؟ إن شاء الله تكونوا بكل خير. طبعا محاضرتنا اليوم حنسجل فيها طبعا المادة، يعني حنكمل فيها المادة اللي بدأنا فيها المحاضرة الماضية، واللي هي بشابتر 2 اللي هي كنا نتحدث فيها عن Cylindrical Coordinates. اوكي، فخلينا نروح للنوتس خلينا إذا نروح للنوتس. طيب إذا وصلنا المرة الماضية عند اللي هو section 2.3. اوكي، واللي قلنا فيه نتعرف فيه على ال cylindrical coordinates. Okay, now let's talk again about the cylindrical coordinates. Make a quick revision. So we said that the cylindrical coordinates mainly are we said rho, phi, and z. Okay, so these are the cylindrical coordinates. Cylindrical coordinates. Okay, and we said that how we define the rho and phi and z is as follows. So this is the Cartesian coordinates to start with. So x, y, and z. Okay, and now we will draw the cylindrical coordinates in a blue color. So we start with rho. Before defining these coordinates, let's draw like a part of a cylinder. Okay. Okay. Yes, so this is a part of a cylindrical surface, and let's assume that the point we are dealing with is lying on the surface of the cylinder, the outer surface of the cylinder. So this is the point P. It has the components rho, phi, and z. Okay. Okay, now let's define these components. So we start with rho. Rho is the radius of the cylinder, of this cylinder, where the point P is. So there is a cylinder, the point P lies on this cylinder. The radius of this cylinder is defined as rho. So how we take the radius? We start at the origin and we go all the way until we get to the point P. Okay, so this is rho. Now we come to the next component, which is phi. Phi, we start, how we define phi. We start at the positive x-axis and then we move counterclockwise until we get to the point P. Okay, so the angle we form as we move to the point P is called phi. Okay, and the last component is z, which is defined exactly the same as the z coordinates in the Cartesian space. Okay, now let's talk about the range of values the cylindrical variables take. We start with rho. Now rho represents, as I mentioned earlier, rho represents the radius of the cylinder. So as it represents a radius, it can't be a negative value. So the minimum value of rho is 0, and it goes to the infinity. It could be any value greater than 0. So rho is greater than 0. Now let's talk about phi. Phi represents an angle in radians. If the point P is on this x-axis, then the value of phi is 0. If we move around all the way until we get back to the same point, we have gone a full cycle, a full circle. So this is the maximum value of phi, which is 2 pi. So phi is in the range from 0 to 2 pi. Okay, and it's in radians. And the last variable, which is z, z is the same as the z we knew in the Cartesian space. And it's, as we mentioned earlier, z could be any value from -infinity up to infinity. Okay, these are the 3 values of the cylindrical space. Okay, let's get back to the nose. Okay, so here in this diagram, we can see the directions of the unit vectors. So here we have the unit vector a sub rho. It goes in the direction along rho, and it has a unity magnitude. The same holds for the unit vector a sub phi. It goes in the direction of the progress of the angle phi, and a sub z is in the direction of the z-axis. Okay, the positive z-axis. Okay, now if we notice here, we can see that the 3 unit vectors are perpendicular to each other. So the cylindrical space is called an orthogonal space, as it happens for these Cartesian space, because all of its axes or coordinates are perpendicular to each other. Okay. So this is the definition of the space variables for the cylindrical system. And yes, okay. Okay, now let's see how we define any vector in the cylindrical space. So in the cylindrical space, any vector A is defined in 2 ways. First, we can define it in terms of its components along each of the 3 directions. So we say A sub rho along the rho direction plus A sub phi along the phi direction plus a sub z along the z direction. Okay, so this is one way to define it. Okay, the other way to define the vector is in the compact form like this. So we have a rho, comma, a phi, comma, and a z. Okay, now if we want to find the magnitude or the length of any vector in the cylindrical coordinates, then what we do is exactly the same way we learned in the Cartesian space. So we take the a sub rho squared plus a sub phi squared plus a sub z squared, and we take the square root of the whole thing. So this is why we can find why we are using the same rule as in the Cartesian space for evaluating the magnitude of any vector. It's because this the cylindrical system is an orthogonal system. So the same Pythagoras rule applies here in the cylindrical space. Okay, now some more things to mention about the cylindrical space is that because the now if we find the dot product between any unit vector with itself in the cylindrical system, I will get a value of 1. So a sub rho dotted with a sub rho is equal to a sub phi dotted with a sub phi, and it's equal to a sub z dotted with a sub z, which is equal to the value of 1. Okay, but if we take any two different unit vectors on the coordinate on each of the main axis in the cylindrical system, then I should get a value of 0. So if I have the dot product between a rho and a phi, it should be equal to 0. The same holds for a phi with a sub z, it's the same. And a sub z dotted with a sub rho, it should equal 0, because what? Because these unit vectors are perpendicular to each other. Each of the three coordinates in the cylindrical system are perpendicular to each other. So the dot product between each two pairs is equal to 0. And now, if we find the cross product between any two coordinates in the cylindrical system, it should not give me 0. Why? Because again, the value or the angle between any two coordinates in the cylindrical system is 90 degrees. So a rho, the cross product between a sub rho and a sub phi should give me a sub z. So we follow the same convention as in the Cartesian system. So you have a sub rho and you have a sub phi, and we have a sub z, and we move clockwise in the cross product to get a positive result. Okay. So if I move this way, a sub rho crossed with a sub phi, I should get a sub z. If I start a sub phi crossed with a sub z, I should get a sub rho, and the cross product between a sub z and a sub rho should give me a sub phi. Okay. Okay, now let's talk about the transformations. Okay, we have two types of transformations between the two systems, the Cartesian and cylindrical systems. The first kind of transformation is the transformation between points, and then the other type of transformation is the transformation between vectors. Okay, Now let's get back to the previous slide. Okay. Let's use this diagram to derive the transformations between the Cartesian and cylindrical systems. So we start with a point P in the Cartesian system with its coordinates x, y, or its components being x, y, and z. And we want to transform this point into its equivalent in the cylindrical system. So P in rho, phi, and z. Okay, so this same point, P, one time I'm representing this point in terms of x, y, and z. And then I want to transform the components of this point into the same point, but with different representation, which is in the cylindrical system. Okay, so the non components are the ones in the Cartesian space, and the unknown components are the ones in the cylindrical system. So we start with the first one, which is rho. Okay, so let's say this is my point, and this point is in Cartesian. So P, X, Y, and Z. So in order to find the equivalent component for this point, which is rho, what we do, rho is equal to what? This is the value of x for the point. This distance is x. And then this distance is y. Okay. So the relation between x, y, and rho is as follows. If we draw y to be here, okay, let's move the point a little bit to make the drawing more accurate. Okay, so the point P should be here. Okay, so this is P in X, Y, and Z. Okay, so this distance is Y. And rho should be the vector or the distance between the origin and the point P. Okay, so this is rho. So the relation between x, y, and rho is using this this triangle. It's a right angle triangle. So we use the Pythagoras rule. So rho is equal to the square root of x squared plus y squared, and we take the square root of the whole thing. So this is how we find rho from x and y. Now we move to the next component, which is phi. We want to find phi using the x, y, and z of the point in the Cartesian space. So how do we find phi? This is phi. We measure it. We start from the positive x-axis until we get to the line rho. Okay, so this is phi. How do we find phi? If we see that phi is an angle in the same triangle, which involves x, y, and rho. So phi is equal to, or we can say tan phi is equal to y divided by x. So phi is equal to tan inverse of y divided by x. Okay. So this is regarding phi, and then for the third component, which is z, z is the same, z here is the same as z here. There is no change. So z in the Cartesian is equal to the one in the cylindrical. So this is how we transform a point from the Cartesian space into the cylindrical space. So this is from Cartesian into cylindrical. Okay. Now, let's do the transformation in the reverse direction. Okay, so we have a point in the cylindrical space, and we want to transform it into its equivalent in the Cartesian space. So we want to perform the opposite process as we have done. So transformation let me just 1 second. I want to fix something with this writing pen. Okay. Okay, now transformation of a point from cylindrical from cylindrical into Cartesian. Okay, so we have a point in the cylindrical system in terms of rho, phi, and z, and we want to transform it into its Cartesian point equivalent, which is P in X, Y, and Z. So this is known, this is unknown. So we want to find X, Y, and Z in terms of rho, phi, and Z. We start with X. How do we find X from rho, phi, and Z? So rho is known and phi is known. We want to find X. So if we say X is equal to rho cosine phi, we get the X component. So X is equal to rho cosine phi. Okay, and for Y, what's the relation between rho, phi, and Y? We say that rho sine phi is equal to Y. Rho sine phi is equal to Y, and Z will stay the same. So the Z in the Cartesian is the same as Z in the cylindrical. So this is how we transform a point from the cylindrical system into its equivalent in the Cartesian system. Okay. Now let's do the vector transformation. Let's assume we have a vector defined in the Cartesian system. So we have V being equal to V sub x, A sub x, plus V sub y, A sub y, plus V sub z times A sub z. Okay, we want to transform this vector from Cartesian into cylindrical. Okay, it's in Cartesian and it's known for me. We want to transform it into cylindrical. To be اللي هو V to be equal to V sub rho A sub rho plus V sub phi A sub phi plus V sub z A sub z. Okay, in order to do this, we use the matrix notation. So what we need to find is the components in the cylindrical system. So V sub rho, V sub phi, and V sub z. Okay. And here we use what we call the transformation matrix. We will fill this matrix up in a moment. Okay, and here we use the vector components in the Cartesian space, which are A sub x, sorry, it's V sub x, V sub y, and V sub z. So this is the output, what we need to find, and this is the input, what we need to use. Okay. This is the output. And this is the input. And this is the transformation matrix. Transformation matrix. Okay, now what we need to do or what we need to put in the transformation matrix. Okay, here in the transformation matrix, what we do is we make the dot product between the unit vectors from the two spaces. So here we have this entry V sub rho represents the first row and the first column. Okay, so what we do here, we multiply. It's a result of multiplying the first row of this matrix with this column. Okay, so what we need to put in this matrix is as follows. Here A sub rho dot with A sub x. This is the first entry. And the second entry is A sub rho dotted with A sub y. And the third entry is A sub rho dotted with A sub z. Okay. Now we move to V sub phi. V sub phi is the result of multiplying the second row with this column. So it's the entries here should be A sub phi dotted with A sub x. And then A sub phi dotted with A sub y, and then A sub phi dotted with A sub z. Okay, now we move to the third component, which is V sub z. V sub z is the result of multiplying the third row with this column. Okay, so what we do here is A sub z dotted with A sub x. And then we have A sub z dotted with A sub y. And here we have A sub z dotted with A sub z. Okay. These are the basic entries of this transformation matrix. Now, what we need to do is we want to put for each entry the actual value of that entry. So let's go to this entry, A sub rho dotted with A sub x. So we have a unit vector along row here. It's called A sub rho. And we want to perform, and we have another vector, which is A sub x, a unit vector on the x-axis. Okay, so this is, or let me do it in a different way. Let me use a different color here. So we have A sub rho, it's a unit vector here along the row direction. So this is A sub rho. And we have A sub x is a unit vector along the x-axis. This is A sub x. Okay, now we want to perform the dot product between A sub rho and A sub x. The dot product is the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between them, which is phi, times cosine phi. So because their unit vectors, their magnitudes are ones, so we are left here with cosine phi. Okay, because the angle between them is cosine phi. So we remove this entry and we put cosine phi instead. So here we have cosine phi. Okay, now let's see the other entry, which is A sub rho dotted with A sub y. So we have a sub rho dotted with a sub y. So this is a sub y and a third vector here in the direction of the y-axis. So this is a sub y. It has a magnitude of 1. And now the angle between, so a sub rho dotted with a sub y, this is a sub rho and this is a sub y. The angle between them is 90 minus phi. So a sub rho dotted with a sub y is equal to what? To the magnitude of the first one times the magnitude of the second one times cosine of the angle between them. The angle between them is 90 minus phi. Okay, now these are equal to 1. Okay, so we are left with cosine of 90 minus phi. Using the trigonometric identities, we have cosine 90 minus phi is equal to cosine 90 times cosine phi plus sine of 90 sine 90 sine phi. Okay, this is 0 and this is 1, and we are left here with sine phi. So a sub rho dotted with a sub y is equal to what? Is equal to sine phi. So this should be sine phi. Okay. Okay, now the third entry here, which is a sub rho dotted with a sub z. Now, because a sub rho and a sub z are both two coordinates in the cylindrical system and they're known to be perpendicular to each other, then the dot product between any vector on the rho direction with any other vector on the z direction, the dot product should be equal to 0. Okay, so here, let's show it here on the diagram. So this is a sub z. If we dot product a sub z with a sub rho, they're perpendicular to each other. So this dot product is equal to 0. Okay, now let's move to the second row. We have a sub phi dotted with a sub x. Okay. Okay, this is the direction of a sub x, and this is the direction of a sub rho. So this is the direction of a sub x. And this is the direction of a sub rho. Okay. And the direction of a sub phi is perpendicular to the direction of a sub rho. So this is the direction of a sub phi. It's in the direction of the progress of the angle phi. So this is a sub phi. Now, the angle between a sub x and a sub rho is equal to phi. But the angle between a sub x and a sub z is what? First, we have to know that the angle between a sub phi and a sub rho is 90 degrees. And we know that the angle between a sub x and a sub rho is phi. So the total angle between a sub x and a sub phi is phi plus 90. Okay, this is the angle we are trying to find. So this is the angle we are trying to find. Okay, it's equal to phi plus 90. Okay, so now we have two vectors, a sub phi and a sub x, and the angle between them is phi plus 90. So the dot product between them is what? So a sub x dotted with a sub phi is equal to the magnitude of a sub x, which is 1, times the magnitude of a sub phi times cosine of the angle between them, which is phi plus 90. Okay, the magnitudes are 1, so we are left with cosine of phi plus 90. This is equal to cosine phi cosine 90 minus sine phi minus sine phi sine 90. So the dot product between a sub x and a sub phi is minus sine phi. So remove this and we put minus sine phi. Okay, now we move on to find the next entry. So here we have a sub phi dotted with a sub y. We have this. So this is a sub phi, and this is a sub phi moving in this direction. Okay, this is a sub phi, and this is a sub y. Okay. We want to find the dot product between them. Okay, so what is this angle? This angle, we can say it is equal to phi. How do we know? We have 90 degrees here. Okay. We have, let me see. So this is phi, this is 90, this is, let's say this angle is gamma, okay? And then this is 90 degrees. Okay, and these two phi and gamma are equal to 90, and this is gamma and this is phi. Okay, so this is phi. Okay, again, let me remove some of the clutter here. Okay, okay. Right. So here we have this angle is phi, okay, and this angle is gamma. Gamma equals 90. Gamma equals 90 minus phi. Okay, and we have, this is y, okay, and this is a 90 degrees angle. This is gamma, okay? This angle is 90 degrees as well. So this is 90. This is gamma, and this angle should be equal to 90. So this should be equal to phi, okay? So now we have a sub y and a sub phi. The angle between them is phi. So the dot product is cosine phi. The dot product between a sub phi and a sub y is equal to cosine phi. So this is cosine phi. Now the last entry is a sub phi and a sub z. Phi and z are two main coordinates in the cylindrical system, and they are always perpendicular to each other. So this dot product between them should equal 0. Okay, so this is 0. Okay, we move to the third row now. So we have a sub z dotted with a sub x. A sub x, the x coordinate and the z coordinate are perpendicular to each other. So the dot product between them is 0. So this is 0. Then we have a sub z dotted with a sub y. Again, y and z are two main coordinates in this Cartesian system, and they're always perpendicular to each other. So the dot product between them is equal to 0. So this is 0. Now here we have a sub z dotted with a sub z, two unit vectors in the same direction. This gives me what? 1. Okay, so this is how we build the transformation matrix. Okay, now we have everything ready for us, and then we can use these matrix multiplication to find v sub rho, v sub phi, v sub z in the cylindrical system. So how do we find v sub rho? V sub rho is equal to what? Is equal to this first row multiplied with this column. So v sub rho is equal to cosine phi times v sub x plus sine phi multiplied by v sub y plus 0. Now v sub phi is equal to what? Is equal to the second row multiplied by this column. So it's equal to minus sine phi multiplied by v sub x plus cosine phi multiplied by v sub y plus 0. And the last thing is v sub z. V sub z in the cylindrical system should be equal to v sub z from the Cartesian coordinate, from the Cartesian system. Okay, so this is how we transform any vector from the Cartesian space into the cylindrical system. Now, the last thing I want to mention is to make the transformation the other way around. So we have the vector in the cylindrical system, and we want to transform it into the Cartesian system. Okay, so to do this, so what we are given here is the components in the cylindrical system. So okay, so we have v sub rho, a sub rho, and we have v sub phi, a sub phi, and we have v sub z. Okay, so this is the vector we know. It's in the cylindrical coordinates. Now we need to transform it into the Cartesian coordinates. So we want to find it in the terms of v sub x a sub x plus b sub y, a sub y plus b sub z, a sub z. Okay, so this is the unknown. Now to do this, we just flip the order here in this matrix. So the output here should be the input here should be the components in the cylindrical, and the output should be the components in the Cartesian. So we have to do the following. So the input here should be v sub rho, v sub phi, and v sub z, and the output should be v sub x, v sub y, and v sub z. V sub x, v sub y, and v sub z. Okay, but here for the transformation matrix, we need to use the transpose of the transformation matrix. We can't use the same transformation matrix to transform from the cylindrical into the Cartesian. We have to use the transpose of this matrix. Okay, and what's the transpose of this matrix? It's simply changing the rows of this matrix into the columns of the other matrix. So the transpose of this is equal, we take, let's call it transformation matrix. Matrix transpose is okay. The transformation matrix transpose, we take the so this is the transformation matrix. We this one, we want to take the transpose of this matrix. We take the rows of the transformation matrix. We turn the row into we turn the first row into the first column. So it becomes cosine phi, and then sine phi, and then 0. Then the second row becomes the second column. So minus sine phi, cosine phi, and then 0. And the third row becomes the third column. So 0, 0, 1. Okay, so this is the matrix we need to use for this transformation. So we remove this and we put the transpose matrix we just found. So this is the matrix we need to use. Cosine phi, sine phi, and then 0. And we have minus sine phi, cosine phi, and then we have 0, and then we have 0, 0, 1. Okay, so according to this, v sub x is equal to what? So v sub x is equal to cosine phi v sub rho plus or minus sine phi v sub phi plus 0. V sub y is going to be equal to v sub y is going to be equal to sine phi times v sub rho plus cosine phi v sub phi plus 0, and v sub z is going to be equal to v sub z. It remains the same. Okay, so in summary, what we have done in today's lecture, we learned how to transform a point from the Cartesian space into the cylindrical space and vice versa. And we learned how to transform a vector from the Cartesian space into the cylindrical space and vice versa. I hope you guys practice these kinds of transformations, and inshallah in the next lecture, the next week, I will, inshallah, we will do some examples applying these kinds of transformations into practical examples. Assalamu alaikum.